name's Alan Dicker, and I'm going to be your guide for the next fun exercise. So let's use multiple tabs, and in one tab, I'll use this tab, we're going to go to the workspace that is for the BV-BRC workshop. So if you know how to get there, I think you've been there multiple times. And we're going to scroll down in the folders in the BV-BRC workshop space to Similar Genome Finder. And I open it by clicking the folder icon on the left. And in this tab, we're going to open this text file. It's a script for the steps we're going to go through on this demonstration. That's the script that we're going to follow. And then in the other tab, go to Tools and Services, the Tools and Service drop-down, and it's in the Genomics section. Right in the middle is Similar Genome Finder. I'm going to click that and open the user interface for submitting jobs to Similar Genome Finder. Oh, the script suggests that we do the following. What we want to do is we're in possession of sequence data for some organism that we've just sequenced. And the hypothetical case is that we are not exactly sure what organism it is that we just sequenced, and we want to ask, what is our genome most similar to? So we can ask the question, what is this bacterium that I just managed to sequence out of tsetse fly or whatever environmental source we collected it from? So the model is we have data. The data are in a folder, and the folder is in that workspace for the workshop that we're currently in. And so I don't know if there's an easier way for me to show people how to navigate there, but if you go to Workspaces and then click on Public Workspaces in that top dropdown, then the problem is there's too many public workspaces, and you have to browse down the list till you get to BV-BRC Workshop, this one. Click the globe icon to the left of BV-BRC Workshop. That's that same working directory that we've been using for the other examples, but we have to navigate to it in this particular way because there isn't the shortcut set up for us in that service window. And we scroll down to Similar Genome Finder. We were just there when we opened up the text file, which is the script that we're following. It's not showing us the text in the document file because it knows that those data types are not what we're looking for. But in this Ricea contigs folder, there might be some data. And yes, lo, there it is. There's a assembled contigs.fasta, and that is appropriate data for submitting to this job. So it lets you click on it. So we've specified the input data, and those are the genomes we're asking, what the heck are they? And what we're going to use is a tool. And let me show you at the top of this page, there's an I in a little blue circle, the letter I for information. When you see that on a web page, you could follow it to find information. In this particular case, I'm going to click on it, and it gives you this pop-up window. And it says that this service will find similar public genomes in the BV-BRC workspace using the MASH min-hash algorithm. And this is actually a link. And if you click on it, it takes you to the publication for the actual computer program, the algorithm that we're using. And the program's name is MASH, and it uses an algorithm called min-hash, which has to do with finding a quick and dirty way of lining up k-mers that are going to give you matches or mismatches to tell you how close or how far away the genome is from the genome you're interested in. I'm going to use the back arrow to get back away from looking at the publication. The back arrow should take me back to my input page, and I have to reload the reads. Scroll down to BV-BRC Workshop, click on the globe, scroll down to Similar Genome Finder, Ricea contigs, enter those. So I've shown you the algorithm, the paper describing the algorithm, and it is a quick and dirty way to line up k-mers that are going to match or mismatch between the set of reads you have or the contigs you have versus the whole database of all of the bacteria. And then there's some parameters such as how many top hits do you want to get? 50 is a good number. If you were doing a search and you didn't see what you really wanted to see in the top 50, you might select a much bigger number, like up to 500. One would be like, if you're feeling really lucky, you might select one. P-value thresholds, if you were getting too many hits, you could limit it by setting a more stringent p-value threshold. For the results we're looking for, we can just leave those at the most permissive value of 1, and the distance of the most permissive distance is 1, or you could restrict it to shorter distances, to smaller distances if you wanted to limit your output. And the scope choices, we can limit it to reference and representative genomes, or all of the public genomes in the database. And we're going to do all public genomes. And we're going to click search or the submit button. And this one should not take long. And this is an example of a job that doesn't take you to the jobs result page. It just formats the results in real time, semi-real time onto your browser right away. Well, I just ran it earlier and it went really quickly. This algorithm that it's running is absolutely fascinating. I think it hashes the k-mers and then it restricts itself to the numerically lowest quadrant of the sorted hashes as a way of, instead of looking at all of the k-mers, and I think that Kraken looks at all k-mers, which makes it fairly slow. This thing speeds things up by having a clever way of making a random window into the k-mers, and that's controllable. You can control how big or small that window is, so you can control the speed. So there is something clever about the algorithm, but it's kind of mathy, but some people are that way. Here's the results. The contigs that we started with were Raicea, and lo and behold, the top hit is of the genus Raicea, as are the top several hits. So all those top ones are Candidatus Raicea. Candidatus is an annoying little prefix onto many taxonomic names that has to do with it being recently named that, and it hasn't been fully approved by the Taxonomic Review Committee that oversees the fate of new names.
How accurate is this similar genome finder compared to phylogenetic tree service?
That is such an insightful question. That's a great question. How accurate is this similar genome finder results versus, say, a phylogenetic tree perspective on what are the closest relatives to the organism that you're working with? And I have to say, and I'm going to point out from some data that's on this view right in front of us, that it really looks like I don't think that this is a really super sensitive, super thorough search through the space, or that the return values they seem a little bit flaky to me. Phylogenetic tree, you cannot build a phylogenetic tree from tens of thousands or hundreds of thousands of bacteria in this database and have it be meaningfully interpretable to visualize, to see yours relative to other ones. So I don't think that scenario works. So phylogenetic tree wouldn't be great if you didn't know where to start. This is a good one for an approximate quick and dirty place for where to get started. And then I would probably follow it up with a phylogenetic tree of, say, the top hits. But look at the scores over on the right, the k-mer counts in the far rightmost column. The top hitting candidate, Raicea genome, has got 99 out of 1,000 k-mers matching. And the next one is 900 and some. And then it's going down to 400 and some when we're still in the genus Raicea. And then down towards the bottom of just the ones I've highlighted, it's 3 out of 1,000. That's like just about to fall off the edge of down to 0, and we're still in the genus. I would think that a sensitive search strategy would hold everything that's at least in the genus to a fairly high score. And then Wigglesworthia comes in because it's a relative. And then there's another Raicea down here below, if you can see that. And I'm going to highlight that one. I'm going to highlight all the Raiceas. That's only 2. And then you skip 1. And then there's another Raicea, and it's also 2. So
those 2 he just clicked, the top ones are all isolates from human body louse. Those 2 are isolates from chimpanzee body louse. And then next, is there another one?
Is there another one?
Oh, there it is up above, the GPBU. Okay, that's the most interesting one of all. That one was isolated from a gorilla pubic louse. So imagine collecting that thing and if that person is still alive. So
Okay, well, what you've just pointed out, Rebecca, helps me feel better about the numbers of matching camers because it makes sense that the top scoring ones are in the same species, Raicea pediculocola.
So question.
Yes. So the question was, for those who couldn't hear it, is there a way to filter or more automatically filter out or find all the Raiceas rather than hunting and pecking and clicking and highlighting them the way that I've done?
genome name the column at the top
Oh,
and it'll sort it alphabetically.
so that's sorting it, I guess, going down.
And if because
And if
they're
you
all
click on it
candidates,
again, it sorts it the other way. So in a way that you can sort them alphabetically and you would be able to find them. Luckily, with Raicea being at the oh, this is candidatus is what's triggering it being at the very beginning. So that's not always going to be great because there's other candidatus get stuck in the beginning of other names. But in this case, it does look like it's all the Raeceas right there. If I was just going to have the data come to me the way it originally came, which I think I would get by clicking on this, I'm just going to go back to my admittedly ad hoc way of hunting and pecking and visually searching for the Raiceas and clicking on them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that is 9. And I know from reading the script that I'm supposed to select those 9 and that what we're supposed to do is go onto the green bar at the lowest icon is called group. And what we're going to do is form a group from these. And we're going to create a new group and we're going to leave it in the genome groups folder. I'm going to call it Raicea genomes 9. And I'm going to save it as a group. And you're supposed to do this too, because in a subsequent exercise, we're going to pull those groups out and do further analysis on that, possibly of the phylogenetic tree sort. There is one more step to fulfilling the script that we're supposed to do here, and I'm going to try to do that so that we have all the assembled data that we need. And I'm going to relaunch the similar genome finder. Actually, I could edit form and resubmit. Yes, we just want to reuse the same submission form, and we're going to use different inputs. And what we're going to look for, we're going to say, I want Wigglesworthia, and the database auto completes that list for us. And I'm just going to.
And see that plot on that? Those are my private genomes. You won't see that. So you're seeing my private data there. So this is to show you how you can look, examine your own data using this, or you can look at my data on that everyone in the world can see.
So when you do it, you're not going to see the long list. You're only going to see 2, right? We're going to select from Glossina moristans. There's 2 reference genomes of Wigglesworthia, and we're going to select the one that's from Glossina moristans. And then for the parameters, we're going to leave the same permissive parameters as we used for the first search and all public genomes. And we're just going to launch the search. And I'll just tell you that the results are just going to be exactly those same 2 Wigglesworthias because there's not like a whole bunch of Wigglesworthias in the database. And this just sort of shows you that that's the case. And it also allows us to create a genome group for those that's going to be used in one of the downstream demonstrations. So here's the results. These aren't the results we were looking for. Maybe it's still sorting alphabetically because it saved the.
Click on that genome name again.
Yeah, well.
Here we are. Look, so it just wasn't sorting. It was an error in the sort mechanism. Look, that one's 1,000 out of 1,000 gamers. The perfect match.
It is. I know. This is the perfect match. So sorted alphabetically, Wigglesworthia comes at the end. So if you click it twice, it sorts it inversely. So that's how we found them. But it's not sorting by Kamer counts when
No,
you click on
not.
Kamer counts.
So that's
Anyway,
the bug.
I'm going to close this out by forming a genome group, a new group, and I'm going to call it.
So you guys need to do this too. We're going to build trees with this, and we're going to do protein family analysis with this.
So I'm just going to call it Wigglesworthia genomes 2 and leave it at that and say add, and then it creates the group in your genome groups folder. You have a special folder for genome groups, and it's an easy way to go and find them. So having jumped through the hoops we were required to, we're done.